Welcome back. Let us continue the discussion on our non-premix combustion, and we are now going to discuss on the CMC model and all this. So, we have looked at different non-premix combustion modeling approach like mixture fraction based approach, where you split the problem into different problem and then assuming the beta PDF you can close the mean values of mixture mass fraction and the temperature. And there is alternative was that the transported PDF approach, and we have seen what are the issues associated with that and how usually we handle that. So, now we are last part of it. One of the advanced model is the CMC model. Again, this is quite specific to the application of non-premix combustion. So, this is where we wanted to just to recap the whole business, and then this will give you a relationship between our exact equation and the modeled equation. Now, this is our equilibrium or presumed jet PDF closure. That means, it is a PDF kind of approach which is computationally less demanding. So, we have exact equations for scalar. This is what we get. From there, we get exact equation for mean and mixture fraction, and from there also we get the variance. That means, this is there and this equation is for variance. So, we get exact equation for that. Now, we get the modeled equation for mixture fraction, modeled equation for the mixture fraction variance. Now, on the other side, this is one side of the whole thing. Other side, you have equilibrium relations between scalar and mixture fraction, equilibrium table, or it could be Flamelet table, and assumed PDF from the PDF mixture fraction, and then you do not have any reaction source term here. In the equilibrium table, the whole assumption is that as soon as things comes in contact, they actually burn and you get the temperature rise. So, this is the burning at jet stoichiometric. This is fuel, this is oxidizer. So, the equilibrium or presumed PDF closure. So, this will give you the complete picture of the whole process, and this portion is the local flame structure, this is your mean variables and all this. Similarly, if you have assumed set mixture fraction PDF, we solve the Zx is fluctuating. So, we need to have a probability distribution function which is to be found. So, the shape of the PDF is assumed and mean and variance we are calculating. So, we get two set of equation, mean and variance, and the variance equation has a production term and a dissipation term, and this is how the effective diffusivity is estimated. So, once we do that, we then see how the whole thing works actually. Flamelet, this is called Flamelet equation or Z chi PDF kind of closure. So, we have exact equation for scalar. So, we get mean, we get variance, and from there we get the model equation. This is the model these things. Now, from the scalar we have a Flamelet equations where all our mass fraction becomes function of Z, scalar dissipation rate, and possibly delta H if the non-adiabatic system. Temperature is also a function of Z, chi and delta H. So, the from there using the scalar dissipation and or the varying strain rate, we get Flamelet library. So, this portion is again pre-computed. That means, this is not done on the fly, this is done a priori, and the calculation is stored, and then the reaction source term is handled in the laminar equation. That means, when we solve this set of equation, this actually takes care of the reaction source term. From here we get the assumed form of the PDF of scalar dissipation rate, and here we get the assumed shape of the PDF for mixture fraction. Using these two, we finally close the presumed or shape PDF or this. Now, another way is that when we want to take into consideration the progress variable C, So, we call this Flamelet generated manifold or presumed ZC PDF closure. So, we have exact equation for scalar. So, we have mean equation for Z and C, we have variance equation for Z and C, and then we get the modeled equation from there. Now, we have an assumed PDF from the mixture fraction, we get another PDF for the progress variable also, and then another side we solve the Flamelet equation, and from Flamelet equation we calculate this library, which is a function of, here we have reaction source term for progress variable and we have reaction source term for mean progress variable from the turbulent flow field. So, we have everything here which are included. Now, using this table and this PDF shape, we get the Flamelet generated manifold or presumed PDF, these things. So, you see how we get the equilibrium things, and this is transported scalar PDF approach. We get exact equations for scalar with detailed kinetics mechanism. We get exact equations for scalar PDF. This is the modeled equation where micromixing term and all this. Then you have Monte Carlo simulation which will give you this, and these are the kinetics mechanism where you need this storage of and retrieval of the algorithm. That is where the ISAT comes into the picture, and this is expensive, and we get this transported PDF approach. And the other one can have Flamelet or transported ZPDF closure, which means that instead of solving this scalar transport or mass transfer equation using the Monte Carlo technique, we can close that using the Flamelet. And how that is done? We have exact equations for scalar. Now, the exact equation for mixture fraction PDF. So, here the PDF is for the mixture fraction. So, that means there is a huge dimensional reduction. Now, on the other hand, we solve the Flamelet equation. That means here we get mass fraction is a function of Z variance and like that. Temperature is also a function of that, which is for varying scalar dissipation rate, we get it and we compute the library. Now, here the PDF function is for Z. So, this is the transport equation or exact equation for the mixture fraction PDF. So, that means instead of, and then the model equations where you use the micromixing model, turbulent scalar flux, and solve this using Monte Carlo algorithm, and using this Flamelet library you get the Flamelet transported PDF closure. So, this is what it is doing. It is taking the advantage of the Flamelet model and also taking the advantage of the transported PDF model. So, what it does, we still solve the, instead of assuming the precept of the probability density function of the Flamelet, we are here solving the probability density function for the mixture fraction itself. So, this is slightly variant or slightly different from the typical transported PDF approach, where you solve for individual scalar equations like mass fraction and temperature in the Monte Carlo algorithm. In this particularly this Flamelet transported approach, here instead of solving that mixture fraction in Eulerian framework, now the probability density function of mixture fraction that we solve in the Monte Carlo algorithm, and using the information of the library we close it. So, that is somewhere taking the advantage of this, and this tells you how there are different approaches which are available, and we have discussed also, like equilibrium. If we just quickly sum up, you have equilibrium based presumed Z PDF closure, then you have Flamelet based PDF approach, you have Flamelet generated manifold kind of PDF approach, then transported scalar PDF closure, transported Z PDF closure. Now, we look at the definition of conditional probability. So, the conditional probability of event A conditional on event B would be equals to probability of event A and B divided by the probability of event B. So, let us say scalars which are other than Z, event A which is phi alpha, which belongs between psi alpha I and psi alpha d psi alpha, and event B eta belongs between z and z plus dz. So, this is how finding the probability of eta. Now, the conditional probability density function, how we define that? F phi z, which is psi z, psi condition on z, equals to eta and d psi. Now, this is how we define f z phi equals to eta psi d eta d psi, and f z would be eta and this. Now, the conditional probability density function density weighted, if we write, that means f of phi, which is condition on z, we can write psi z equals to eta. That means when z equals to eta, we will get the probability of this function. So, this is where you get the conditional probability. That means you try to find out the probability density function when z equals to eta, and this is how you define the density weighted conditional probability. And conditional mean, similarly for any quantity, let us say g, when it is conditions at eta, it would be g integration of g phi f phi at condition at eta and d psi. This is Fabry averaged. So, this would be like this, and then g eta 1 by f z, g also d psi. So, one can find out the mean g will be 0 to 1, g condition at eta and f z eta, so d eta. So, this will give you the mean variable for any quantity and like that. Now, if you look at the conditional mean and fluctuation of species mass fraction. So, let us say we try to find out the conditional mean or the density weighted mean of q alpha. So, this would be y alpha at z when it is eta, and conditional fluctuation would be y alpha for q alpha plus y alpha fluctuation. So, the conditional correlation that will remain y1, y2 at z, y1 at z and y2 at z. So, this is the correlation that one has to find out. Now, we will transform the scalar transport equation. So, this is on mixture fraction, this is mass fraction. Substituting y is q plus y double prime and taking the conditional mean, we find out an exact equation for conditional mean q alpha. So, application of the chain rule, y is q and y prime, del y by del t would be del q by del t, del q by eta, del z by del t plus del double prime by del t, because q is now del y by del I xi, del q by del xi, del q by eta, del z by del xi and del y by del xi. So, this is exact equation of the conditional mean. Now, the transformation of the diffusion term, similarly we use y is q plus y double prime. So, we write delta rho d delta y equals to rho d delta q plus del q by eta delta rho d delta z. So, again we are using the simple chain rule for the derivative, and what we get rho d delta z square, which is again the second derivative of del q by del eta 2, del 2 q by del eta 2 and rho d delta z into delta del q by del eta. So, this is an term for the diffusion term that you get after replacing those conditional information. Now, when you go to exact equation of the conditional mean, so we putting those back, rho eta del q by t, rho eta v which is condition at eta dot del q plus rho eta n condition at eta. So, this is a term what you get. Rho eta is a conditional mean density, not density weighted. So, mind it, this is rho when z equals to eta, that is a condition. N is d delta z square, this is a scalar dissipation rate. EQ, which is a terms related to diffusion in physical space, that means this term. EY, which is a term of conditional fluctuation. Okay. Now one can look at the equations of this paper in PCS, Progress in Energy and Combustion Science. About there is this particular literature which is quite important, which will give you an complete idea about this CMC model description and all this. So which will let you to get into these details. These are now, if we come down to the exact equation for the conditional mean, you have the notation of the Cambridge group. Using the similar notation, we write Q alpha equivalent to Y alpha eta, that means this is the conditional mean. So our equation will become del Q T by del T U J del Q alpha. So this looks like and similar to our convection term, and the total left hand side looks like an derivative, total derivative, but obviously it is conditioned at eta, n eta del T Q alpha. So this is looks like an conditional density, a conditional diffusion term. This is a reaction rate term, conditionally filtered reaction rate term, Andy-Love scalars and other terms which are neglected. And what EF contains, Y1, U1, Y alpha eta conditioned, and U1 eta and Q alpha. So this is the term which has to be closed. So if we see how this conditional moment closure things and the connectivity between different these things, we can quickly see there is an exact equation for the scalar. Now from there you get exact equation for variance of the mixture fraction, and then you have exact equation for mean of mixture fraction. So this is what you get. This is mean, this is variance, that means this is Z, this is variance, and exact equation for conditional moments of reacting scalar. So these are conditional mixture fraction and all this. From there you get the mean quantity or model equation for the mixture fraction, for the variance and the conditional moments. Now you have an assumed PDF for the mixture fraction. Here you can have model's equation for scalar PDF, and which goes to the modeled equation, and using these two information you finally get the CMC closure. So this is slightly different from the other things that we have already discussed, because this uses a different sort of an information to close terms and like that. So that's why one has to be bit careful, because this is also bit involved computationally. This is also slightly, I mean this is not expensive like transported PDF approach, but this is also quite expensive computationally, and but provide you very good predictions. Now from this literature, the table that, and this will give you an idea what we do when you look at the presumed filter density function or PDF function. There you solve for Z variance, C variance and all this, then you have closures for all this like gradient diffusion assumption, and then finally source terms are closed like an using the PDF function. Now the details you can find out this literature. Now the when you come to, so this table actually quite good or informative in the sense this is actually taking into account the kind of discussion that we have had, the different kind of, like this is G equation for premix case, flame surface density for premix case, flame wrinkling factor, thickened flame. So these are the models which are actually for premix case, and they compare how they compare to each other. Then we come to the non-premix case and we can compare how. So this is when the CMC you have conditional mean, mass fraction, then the conditional at Z and C, and then you actually close these terms or condition terms, and then finally close the source term. So this is how in CMC you take into account. Now, when you go to transported PDF, you have solved for f xi, f eta, f psi k, and then you close these terms using your information, and finally you get those reaction source term closure. So, one I would suggest that should go through this particular literature. This is in progress in energy and combustion science in 2012. This will give you an good overview of all these models that we have been talking, and how there are different terms which are unclosed and how they are closed. So, sort of getting you a nice overview of everything. So, that is what this is important. This is because already you can see upper half talks about the premixed case and the lower half talks about the non-premixed case. Specifically, if you look at this, again as I mentioned, this is theoretical description or theoretical system. It is suggested or it said that it can be applied to any mode of combustion, but when it comes to the application of premixed combustion, it requires some fine tuning, especially in the mixing model term. I mean, rest of the terms appear to be okay, but when you apply to this one in the premixed case, so you require tuning or modification to mixing model, because the mixing model thing or the concept of the mixing model is actually, or mixing is missing in premixed case, because in diffusion flame one of the ideas is that your fuel and oxidizer are injected separately. So, they come through the molecular mixing, and then along the jet stoichiometric the reaction takes place. But in premixed case, everything is injected by premixing. So, the fuel and air, they are premixed. So, that is why the concept of this mixing model is little bit not that trivial to be applied in a case of premixed combustion, and that is why. And there are few literature where they have, people have tried to modify in terms of a premixed flame how one can do that. So, that is another important aspect of it. Now, just to to conclude before these things, we will look at the now, because all of our discussion pretty much kind of restricted looking at the RANS framework, but in the LES case this would be filtered function, where the filtered field would be a integration of A, and this is the filter. This is the filter which you use. So, the definition of unresolved part, which is A prime, would be A minus A mean, and if you normalize the filter, this should satisfy this property. And there are different kind of filter, and there are box filter. So, this box filter, what it does, it is a spatial averaging over a box size of delta. So, that means this kind of things. Then there could be Gaussian filter, which looks like an distribution of an Gaussian kind of distribution over a filter size of delta. Then once you define some filter, you can actually define some density weighted filtering. The density weighted filtering will look like rho A bar by rho bar, where rho it is integrated over filter, and this is. So, this is what one has to use, again because it is a reacting system. So, instead of this, the density weighted filtering is what is more appropriate. Then your resolve, this is similar to that RANS things where we have used density weighted average. Here we are using density weighted filtering, so that you get the effect of density due to temperature variation and so. Now, if I derive the filtered density function, this is filtered density function from the filter, can the filtering process be interpreted as averaging with the respect to probability density function? So, that is a question and we can see whether it is true or not. So, this is our mean, and the mean is obtained like A and G delta. Now, this A one can write is that the A star delta of the A star. Now, once we put that back, that mean of A will become double integration of A star delta function d A star and the filter function, which will become this quantity. If we take into the bracket, and the mean will become with the filter density function defined F A, which is then delta function and G delta function. So, that is what one can actually replace this filtered quantity by a probability density function. Now, the filtered density function is essentially filtered value of a direct delta function. So, if you have this A, which is an A and G delta, so filtered value of the physical field would be the spatial average of the physical field with filter function as a weight function. So, this is an weight function kind of, it is an essentially, though we are talking about so many mathematical description, integration and all these things, but it boils down to an, this is an important statement, it is boiled down to a numerical integration of some weight function. So, the probability function would be defined as the delta function. So, the value of FDF at point in composition space would be the filtered value of the direct delta function. So, all these different kind of delta functions, they are nothing but just sort of you can think about the different over a filter size of delta, the way the weight function is used to get the filtered quantity. And now, similarly, like your RANS framework, this is an example of these things one can use also in LES framework in CMC. So, CMC in RANS is itself quite computationally expensive, but when you go to in LES it will become more computationally expensive. So, that the price you pay, but this can provide you good prediction compared to. So, if you have presumed PDF, so the CMC would be better or rather sometimes equivalent to transported PDF. But if you look at the computational cost, this is the low cost, here the cost would be high, here the cost is much higher. So, the cost wise also, but this can provide you very comparable result like a transported PDF approach, but it is, that is why it is equal, but this is very specific to non-premix case. So, now once you go to LES situation, this will actually be more this thing. So, the FZ what you have, this you can use the delta function with this filter function and the probability distribution function, which could be written like this, and finally, the condition one can write like that. So, that is how you can define these CMC equations in RANS and LES framework. So, that is pretty much concludes the discussion on our gaseous part of the combustion modeling, where we have looked at premix and non-premix. Now, we will stop here today, and we will continue the discussion for multi-phase flow in the next lecture. Thank you.